Good day. How are you doing today? So in this lesson, I'm going to show you how to do parametric differentiation. So you might be asking yourself, what is parametric differentiation? So if you are given two equations, x is equal to t cubed plus t, and y is equal to t squared plus t. These two equations that you're given, x and y, they are related with the variable t. So this third variable is common in the x and y function. So therefore, to find dy dx, we'll say dy dx will be equal to dy dt. We differentiate this function, we get the dy dt, then we multiply that by dt dx. But remember, we've got x, so we actually do the dx dt. Then we inverse it to get the dt dx, then we multiply. That's how you do your dy dx. So to finish off this, dx dt is equal to 3t squared plus 1, and dy dt will be equal to 2t plus 1. Therefore, dy dx will be equal to dy dt multiplied by dt dx, which is equal to dy dt is that one, which is 2t plus 1 multiplied by 1 over, because the dt dx is the inverse of this. So that we inverse that, then we get the dt dx, which is 1 over 3t squared plus 1. And that can be simplified further as 2t plus 1 divided by 3t squared plus a 1. And that's how you determine your dy dx of two parametric equations. Now, moving on to the other example. Now, in this example, we are asked to determine dy dx for the parametric equations. X is equal to 2t to the power 4, and y is equal to t cubed plus t. So these, again, are parametric equations which are related with the variable t. So we just do dx dt is equal to 8t, and dy dt is equal to 12t squared plus 1. Now remember, dy dx is equal to dy dt multiplied by dt dx. So that is equal to your dy dt is that one, which is 12t squared plus 1. That multiplied by, remember, the inverse of that, because we don't have dt dx, we've got the x dt. So to determine dt dx, we just find the inverse of 8t, which is 1 over 8t. And that can be simplified further as dy dx is equal to 12t squared plus 1 divided by 8t. And that's how you do this question. Now, moving on to the second example. So we got another two parametric equations again, related in terms of t. So to find the dy dx, first of all, we do dx dt is equal to 4t cubed minus 6. Then dy dt is equal to 3t squared. And remember, dy dx is equal to dy dt multiplied by dt dx, which is equal to 3t squared. And once again, we want the inverse of that. That will be 1 over 4t cubed minus 6, which is equal to the dy dx is equal to 3t squared divided by 4t cubed minus a 6. And that's how you do this question. Now, moving on to the third example. So in this example, we are asked again to find dy dx of the two parametric equations. We do exactly the same thing again. Repetition. Dx dt will be equal to 2t. Remember the derivative of sign, it's a positive cos, so that will be minus cos t. And dy dt will be equal to, here the derivative of a constant is 0 and derivative of a cos is a negative. So that will be negative sine t. And therefore, dy dx is equal to dy dt multiplied by dt over dx, which is equal to dy dt, it's minus sine t multiplied by the inverse of that, because we want the dt dx again. So that will be 1 over 2t minus cos t. And that gives us our dy dx equals to negative sine t over 2t minus cos t. And that's how we do this equation. Now, moving on to the fourth example. Once again, we've got a trigonometric equation, and the parameter here is theta. So these two equations, they are related with theta. So we do again the derivative dx. In this case now, we are deriving with respect to theta because the theta is the variable, not t. So dx d theta is equal to, remember, the derivative of cos. That is negative sine. So that will be negative 3 sine 3 theta. And here dy d theta will be equal to the derivative of sine. It's a positive cos. So that will be 3 cos 2 theta times a 2. So that gives us a 6 in front here. So that will be equal to 6 cos 2 theta. That's our dy d theta. Now, dy dx will be equal to dy d theta multiplied by d theta dx. And that is equal to the dy d theta, it's 6 cos 2 theta multiplied by d theta dx, of which here we invert that again, and that will be 1 over, so it's just negative 1 over 3 sine 3 theta. So that will equal to, so our dy dx will equal to 6 cos 2 theta negative divided by 3 sine 3 theta, which can be further simplified to be negative 2 cos 2 theta divided by 3, no, not 3, it's just divided by sine 3 theta. That's how we do this example. Then moving on to the final example, example number 5. So the parametric equations of a curve are x is equal to 4 sine t, y is equal to cos t. Show that dy dx is equal to negative sine t. Now we do exactly the same thing. So dx dt is equal to, here the derivative of sine is positive cos, so that will be 4 cos t. Then dy dt is equal to, in this case, derivative of cos, it's a negative. So it's a negative 2 sine 2t. Now, then the dy dx is equal to dy dt multiplied by dt dx, which is equal to, in this case, our dy dt, it's negative 2 sine 2t multiplied by the inverse of that, because we want a dt dx. So that will be 1 over 4 cos t. And this can be simplified further. Dy dx is equal to negative 2 sine 2t divided by 4 cos t. But however, we are asked to simplify this further to get minus sine t. So this can be simplified by applying the double angle of sine here, and that becomes negative 2 multiplied by 2 sine t cos t bracket divided by 4 cos t. So the dy dx is equal to that. And this can be simplified further to be, you cancel out the 4 and the cos t, then you're just left with a negative sine t. And that what then we write just shown. And we have shown that the dy dx is equal to negative sine t. And that's how you do your derivative of the parametric equations. I hope to see you again in the next lesson.